Hello and welcome back to Differential Equations, section 1.4, separable equation for like 5th time in this course. So you learned this thing in Calculus 2 and then in the past 3 lectures. So I really have nothing to add. You understand that the method is the method depends on separating variables, put all of the variables of one kind on one side of the equal sign, all the variables of the other kind on the other side. Constants can be either way, and you hit both sides by integral, and then from there follow algebra to solve it. One thing that you have to be careful of is that you will not always get explicit form at the end. So some of your answers will actually not be functions. There will be solution curves. They will not be functions. We're going to work on a few examples and then just move on to the next section because I guess we can. The idea is to separate variables. Let's take a look at examples from homework. If I hit the homework exercise that is assigned, just move one over. Now, problem solving is important. Problem 6 has this really interesting situation. So dy dx is equal to 3 square root of xy. Again, in the previous 3 lectures, I explained all of this, how it works. So now we're just going to take a look at a few examples real quick. Observe that we have 2 variables, independent variable x and dependent variable y. The goal is to separate variables. We have these guys on the pile. Is there a way for me to separate x and a y algebraically there? What can I do? Then you will have a derivative squared. That would mess up integration. How can I separate x from y there? You have x to the 1/2 times y to the 1/2. Yes. So we can separate this by giving each one of these its own root, which is what you said, x to 1/2 and y to 1/2. So now we have the differential equation. 3x to 1/2, y to 1/2, and we are going to move the, so 3 can stay anywhere, that doesn't matter. What matters is that we are going to have y to the negative 1/2 dy is equal to 3x to the 1/2 dx. And
the rest of us are coming.
Good evening. Yeah. It's like the entire rotor rack just walked in. So what we have is the now integral on both sides. And we integrate. So on the right-hand side, we are going to get y to positive 1/2 divided by 1/2, which is the same as times 2. And on the right-hand side, we have 3x to the 3/2 divided by 3/2. The 3's will die. We have plus c. We said that last time. It's not there for decoration. It's very important to have it. And now we also see that these 2's cancel as well, and we have y to the 1/2 times it's exercise, man, it's exercise, cardio, x to the 3/2 plus c, and that will be the solution. Now observe that you have y to 1/2. This particular one you can fix in this case by squaring both sides. Hey, come on. So we square both sides, and we just get our y of x is equal to, on the other side, you could FOIL if you want to, but then you don't have to. So you can leave it in this form. Now, we can check the answer. Right, so this would be general solution. I did not have at the beginning, right, the problem, I did not have initial condition, so I don't get to solve for particular solution in this case. So this is what I have. Again, we started with the problem, separated x and y so that we can do separation of variables, and then put all x's on one side, all y's on the other side, and then integrated both sides. So it's a process that you have seen 50 times. Alex?
Is this straight?
Yes.
Oh, hi, straight.
Well, late on that.
Yeah.
Wait, was there a notification or something saying that you're going to be in this room?
You said it on Thursday.
Yeah,
We were there for about 5 minutes.
that you were going to be down in the basement.
Starting Thursday, yes.
You looked out there, where
No, starting Thursday.
You said that you'd meet here.
Yeah. But yeah, the other week I said, because this was supposed to be our new room for Tuesdays, which we are going to now give up because the projector is swapped in our original room. So starting Thursday, starting Thursday, in 2 days, we will be in CO8 for every class until, including the final. So that's it. Starting Thursday, we will always be in CO8. We'll see how well is that going to work, because there is a classroom next door with that soundproof wall. Yeah. If you want to check if this solution is good, you will differentiate and plug everything in and see how this works out. Another example. Let's see. So here's a nice practice for you guys. It's 27. I know how much you love exponential functions. So dy dx is equal to 6e to the 2x minus y. And we have initial condition y of 0 is 0. So let's get busy with the separation of variables and So how do we separate this e? What should we do? Anyone?
Separate the e to the 2x minus y is the same as e 2x times e minus y.
Nice. So the next step, if you are stuck on algebra and you shouldn't be, is 6e to the 2x over e to the y. And now you can separate the variables and then hit the integral. And okay, let's see. So no, we have to, well, you have this, right? We are looking for a particular solution. So your solution should not have a constant, right? Because we have initial condition there. Okay, let's talk about this. So we have e to the y dy equals 6e to the 2x dx. And then we hit this with integrals, with smile, right? Because we're happy. It's calculus. There we go. Thank you. So, called the gallery of smiles. So now the integral of e to the y is e to the y equal, on the other side we have 6 is a constant, copy that. The integral of e to the 2x is, that's the derivative, plus c. So e to the y is equal to 3e to the 2x plus c. Now what? Exactly. ln. Now what? What should I do here? Nothing. Okay. Well, let's see if we can pull off some witchcraft and make this work, because we might be able to. Can we? Nah. Well, we are going to calculate now that. So we also have y of 0 is 0. That's the initial condition, which means that if our x is equal to 0, y is equal to 0. That's the meaning of the statement. It's like a point, x comma y, 0 comma 0 in this case. So y0, ln of 3e to the 0 plus c. So 0 is equal to ln of 3 plus c. We are going to e both sides because we have to get rid of the ln. E to the 0 is 1. And then on the other side we have 3 plus c. So c is equal to -2. This over here was general solution. And now we're going to replace this c with -2 and obtain particular solution for the problem. So y of x is equal to ln 3e to the 2x minus 2. Great. This is a typical exam question. This one, like you can start this one. This is a typical exam question on separation of variable where you don't have integration by parts followed by partial fraction decomposition for integration. It clearly outlines the procedure for separation of variables. It outlines the procedure to figure out a particular solution of the problem. Has you know, a little bit of the algebra sprinkled on top. So this would be the representative question. The next part is Newton's law of cooling. It's a derivation, it's a formula, and this could be your first project if you choose so. What you would need for the first project is a chicken or a turkey, but obviously if you are a vegetarian, use the chicken. And you can run this experiment in your kitchen. Or you can do the rocket, which is the problem in the book. If you choose to do this project, the first project, as Newton's law of cooling, you will actually write this derivation to derive Newton's law of cooling formula, and then you would use the temperature probe to do calculations and set the timer for cooking. I've done this. It works perfect. My students have done this in the past. It works just fine. You need that temperature probe that you can poke into, right, to tell you what is the temperature inside of the whatever you're cooking in the oven. And also you will be reading the temperature of the oven from the scale of the oven. So it's not 100% right accurate, because none of those measuring devices are extremely accurate, but you are going to get a very good, precise answer. Now, the reason why I'm saying that you can do this, it's very cheap to do something like this, because you can get the whole chicken in ShopRite for $4, $5, right? So obviously don't get the cooked one, you get the uncooked one. So you know, put some seasoning on it and just dump it in. You can also take that to the next level. Let's say it's wrapped in bacon, and you can see that actually that doesn't work. because the heat conductivity of a bacon is yeah, much higher than the chicken, and then you get.
What if you put in the microwave?
Well, it's a completely different way of cooking. So yeah, you would have to actually first cook the chicken, then wrap it. It's a project. I did it in the past projects. So we're going to do derivations for Newton's law of cooling, and then you can apply it to try and cook. And it's, guys, really awesome when it says, you know, it's going to be done in 48 minutes and 15 seconds. And you just go, beep, 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 48 minutes, you just walk away, come back. It's perfect. It just, you know, it's with a few percent margin of error because, again, all of the measuring devices you are using and I'm using at home are not, you know, lab grade. But this experiment works. And students have been doing this for the last 3 or 4 years in various classes. So you can opt to do that, or you can opt to do the one with rockets on whatever page is, as project number 1. The projects don't have to look like the ones from your calculus courses. However, impress me, you can do that. Let's take a look at Newton's law of cooling. This law is actually law of cooling and law of heating as well. It is well tested. It works perfect. We write, this is the standard situation where you take the words, you write the differential equation, you solve differential equation, in this case using separation of variables, and you get the formula which you can use to cook chicken or whatever. So let's see. The time rate of change of temperature T of a body immersed in a medium of constant temperature A is proportional to the difference A minus T. So the time rate of change of temperature, I'm just going to say rate of change of temperature T in time T in room temperature. They use A, so I'll keep that, is proportional to the difference A minus T. It should make sense because if you have a cup of coffee that it's 120 degrees and you are in a 70-degree room, right? It's 50 degrees difference. It will take longer to cool than if the temperature of the coffee is 120 degrees, but the room temperature is lower than that, right? So you have more. You also have to understand that when your coffee or tea or chicken are cooling, they give off heat which mixes with the heat of environment which rises. So it's the same law of action-reaction when the heat exchange happens, right? When you push an object, object pushes back, right? The reason why you are sitting on the chair is because the chair is pushing the same weight up. If you exceed the weight the chair can push up, chair breaks. So the bridge works the same way. We know what the weight, right, limit is for the bridge. They say no truck over 5 tons. Well, that means no truck because the bridge can't push up 5 tons. That's the reason. So for cooling, same principle applies. Your coffee will be heating the room, but when you look at the coffee, the volume of the coffee and the volume of the room, it's going to be almost insignificant, the change of temperature. right, in a room. But obviously, if we bring 150 coffees, right, that are 50 degrees more, we are going to detect the change in temperature because, right, it's a lot more heat introduced to the system. So now, when you are writing the differential equation here, it says the rate of change of temperature in time, so that's change of temperature in time, is proportional to the difference between the room temperature and the temperature of the object.
So can we see like the proportional?
Yes, that's the constant of proportionality, and we will see exactly what it represents by the time we are done with the derivation. Now we are going to separate variables. So we have dt over a minus t equals to k dt. Again, k is the constant, so it can go on any side. Just leave it where it is. Integrate both sides, whether you integrate in front or after k, doesn't matter. K is constant. We are going to get negative ln a minus t equals to kt plus c. Note that negative in front. Guys, your variable of integration is t. And if you are to do u sub, you would see that the derivative of a minus t is -1, right? And that's where that negative comes from. So you either know this or you don't know it as a shortcut. You can do u sub on the side if you don't believe me, but this negative is not there for decoration. All right? This negative here is there because you're integrating negative t. A is a constant, so you're integrating negative t, and if you do u sub, you will find that -1 that you need.
So that's always if you have that negative.
On this one, yeah, on this one, if it's a negative t, yep. And now we are going to follow our, we're going to follow algebra, right? We are going to say that this negative goes in. We get ln of 1 over a minus t equals to kt plus c. We are going to e both sides and get
You put 1 over a minus t to get rid of that negative?
yes, in the ln makes the reciprocal, right? It goes in as the exponent, and then exponent of -1 flips. So we have 1 over a minus t is equal to e to the kt plus c. Yeah, that will give you another constant. So I'm just wondering if it's better if we, yeah, no. It's better if you actually move the negative to the other side. If you move negative to the other side, then you have solving for temperature from here will make more noise. Kill. Move the negative, so you have ln a minus t. That's better. So move the negative to the other side. Get negative kt. You can put plus c again because the negative on c gets absorbed by the constant. You don't have to change that sign into negative c. And we will see that happening over and over and over the course of the course. And now e both sides. There we go. So now we have a minus t is equal to e to the negative kt plus c. And from here, if I move a to the other side, it becomes a negative a plus c, and then multiplied by -1. So t as a function of time is going to be a minus e to the negative kt plus c. I hope.
Oh,
Of course, it's math. And now we need initial condition. Initial condition is the temperature, the initial temperature of the poor thing that is in the oven or coffee in a cup. So we will say that T of 0 is T0, that's initial temperature. And we can plug this value, right? Well, first I'm going to deal with the plus C situation, right? So T of T is equal to A minus e to the negative kt times e to the c, right? And we can call this some new variable, whatever you want to call it. So T of T is equal to A minus C1, whatever, e to the negative kt. So now what happens is you will place zero for time. So you get T0 here, right? Because T of 0 is T0, T naught. A minus C1. So you can see that C1 is T0 plus A. C1 is A minus T0. And we plug that here for C1, giving us the Newton's law, which is A minus T0 times e to the negative kt. And this is Newton's law of cooling. We have T of T, temperature at any time. We have A, room temperature. So if you are working, or if you're baking something, that's the temperature of the oven, because that's the room in which the chicken is, right? And then you have T0, which would be the initial temperature of the chicken. That's the temperature of the chicken before it goes into the oven. No, well, that would be the room temperature of the kitchen. You see, Newton's law of cooling deals with heating or cooling. So, if this is a cup of hot coffee, the room temperature is the room of this temperature, of the temperature of this room, right? So, because that's the medium in which the cooling occurs. So your tea or your coffee is cooling in the room temperature, and the room temperature is the temperature of the room. But if you are baking a chicken or turkey or cookies, the room temperature is actually the oven, because that's where the heating is happening. So let's say your chicken had to thaw out, right? That's also the Newton's law of cooling formula, because the temperature of the chicken is changing from being frozen into not being frozen. So that's one problem that you can solve, and you can exactly calculate how long will it take for it to thaw out. And the room temperature that you use would be the temperature of the kitchen, because the chicken is on the frozen chicken is on the counter. But when you are ready to bake the chicken, the heat change happens in the oven. So oven becomes the room temperature. So let's say your oven is at 375. You use 375 as the room temperature. And the initial temperature of the chicken would be the old room temperature of the room, because when it thawed out, it became the same as the room of the kitchen, right? So it's a little bit convoluted, but when you think a little bit about this, right, you see how the room temperature is actually, the room temperature is the temperature of the medium in which the temperature change occurs.
Oh, okay.
So whether it's the room where the coffee is cooling, or it's the oven where you are baking. Room temperature is whatever it needs to be.
So wherever the change is going to happen.
Wherever, yes.
It's kind of unrelated to that. It is. But if we're solving for time, what's the basis in the context of chicken? What is the temperature of chicken that we are solving for time?
Well, you know the target temperature of the chicken and turkey needs to be 106. Maybe you don't know. I know.
That's what
So I know that the target temperature is 160. So you will have the target temperature, and you have the room temperature of the oven, and you have the initial temperature of the chicken, which you took before. The only thing that you don't have is this K, which is different for everyone, because that K, the constant, depends on the type of the oven, the size of the chicken, and so on, and you have to obtain that every time. So, clearly, turkey will take longer than a chicken in the same oven at the same temperature, because it's bigger. That impacts K. So, you start this problem by tossing the thing into the oven, waiting 30 minutes, right? So this is 30. If you want to do a problem in minutes, if you want to do it in hours, then it's 0.5, right? So you're waiting. I would rather do it in hours because the conversion, right? But you can do minutes and then 122 hours. So now the first thing you have to do is you measure the chicken before it goes in the oven. You have these components. You wait 30 minutes and you measure the temperature of the chicken. And that will be initial conditions. So you have the temperature of the chicken after 30 minutes. You have the room temperature of the oven. You have the initial temperature of the chicken, and you have the time 30. Clearly, this is the only unknown. From that measurement, you make one measurement, let's say 30 minutes into baking. You will be able to actually run this through, and then you have the all of the information, because then for your final time, you know that you want to have the 160 here. Let's say it was 92 degrees when you checked it, right? The chicken going in was 67 degrees, let's say. You waited 30 minutes, it was 92. You have to go all the way to 160. So the final calculation is then you have this at 160, this 375, 375, started at 67. You know what the K is because you calculated from the initial condition, and then you can compute time for all that. I actually think that I posted on my Instagram when I did it the last time for Thanksgiving last. Let me just check. If you zoom, I have to keep up with Rotary. So.
Oh, okay.
Do I have it?
So, like in our project, we're going to try to figure where.
Well, if you are going to do the chicken, what did I do? So here are the calculations. Zoom in. So this is the turkey calculations that I did for the turkey that I used. Worked out to be 2 hours, 35 minutes, and I believe 12 seconds or something like that. That's like one of the two main things that are there.
So, but are we solving? I'm guessing we're solving for time, right?
Yes, yes. You want to see. So once you solve that, it will take, let's say, 2 hours and 8 minutes to bake your chicken. Don't forget to take away 30, right? Because right?
Right,
And
we
whatever
want to take
and whatever
additional
time it
conditions
took
so
you
we can
to
figure out,
get those calculations, right?
Okay, right.
So let's say you toss the chicken in at 1 p.m. At 1:30, you do the measurement, and then maybe it takes you another 5 minutes to solve the problem. So you will be taking the final answer, subtract 35 minutes, let's say,
Yep.
and you set the timer for the remaining time. At the end, perfect. You know.
When everything's black.
Well, then your math is off. I mean, what can I see? This is how you start cooking, right? You show up in the kitchen with the TI-83 and the pan in the pan, right? Everyone else knows they need to evacuate, right? They will recheck and check the fire detectors and all of the things, right?
Yep.
The 911 will be punched in the phone up to the point where you have 911 already. And that's it. And then from there on, it's just cook. And it works. Yeah.
Well,
You can also do the mixture problems with soup and stuff.
what if I were to do with a fryer? Does it have to be conventional?
No.
Can I do it with a fryer? I guess.
Yeah.
Okay, cool.
French fry.
That's what I'm gonna do. I'm gonna do French fries because I work in a kitchen, so I'm gonna try French fries.
But why are you complaining? You work in the kitchen. You can
I
do
know.
this.
Yep.
Wait, I thought your job was to jump on airplanes.
I have two.
Oh.
At night, I work in the kitchen.
What he does, he takes a poor person that's afraid of heights, straps a key, and just jumps out of an airplane. That's what he does.
Oh, it's not perfect. You have to check it every year. So.
That's better than shooting.
I know.
Well, they have the annual checkups on the planes. And
Annual?
Well, that's because they only fly once a year. That's why.
No. Every plane has to go through an annual checkup. It's by law. So that's why I say they're not perfect, because you have to go through a checkup.
All right, that's enough of this. So I'll restart the stream for the next section. But yeah, I'm a little bit concerned. Oops.